We're not going to spend much time talking about complex laminar pipe flows. You can do the same process with laminar pipe flow. It hasn't been an area of much interest in engineering because laminar flow in pipes doesn't occur for almost any of the fluids that we work with at a macroscopic scale. Recently, however, people have become more interested in laminar flow in pipe networks because of microfluidics. And so microfluidics is a growing field. It's been very, very hot for the last 20 years now. And people are making smaller and smaller devices, particularly in the bio area, the bioengineering area, to really handle individual cells so they can move individual cells, test individual proteins. And basically these devices are extremely small. And in these very small devices, you do get laminar flow. And some of the flow patterns are now pretty complicated. So there is an increased interest there. And so there's been some more research on trying to extend this complex pipe network flow stuff to laminar situations. If you look at the behavior, it's quite different. The big thing here is that for uh, laminar situation, this is still the loss coefficient, now LAM to indicate laminar. It's going to have a totally different value for laminar flow, and it's multiplied differently. So it's multiplied by mu and u, not u squared, and divided by d. That's the same as it was. And we can put that into the same kind of formula that we used for turbulent flow, delta P, rho G, delta Z. But now we have the friction loss because of the pipe itself, which is mu ud over times 32 L over D. This comes from the fact the friction factor for laminar flow, we proved in an earlier lecture, was 64 over the Reynolds number. So you can show that that comes out to be this when you put it all together. And then you have just this K laminar, the sum of the K laminars here, just like we did for the turbulent situation. The big difference here, I mean, there are a couple of differences. As you can see, we're not multiplying by rho anymore. We have mu instead, and we have u, but not u squared. So very different because we have u here instead of u squared. Here are just some examples of some laminar Ks for very low Reynolds numbers from 1 to 10. For a 90-degree bend, apparently K is 0.5 in the laminar regime. For 2-to-1 pipe contraction, K is 7.3. For 2-to-1 pipe expansion, K is 3.1. So generally large K values. Laminar flow has large friction effects. Of course, the friction is reaching all throughout the pipe, so that's not surprising. For these contraction and expansion relationships, you do need to use the smaller diameter velocity when you're applying it in this formula. So you need to use the one for the smaller diameter, which gives you the higher velocity if you were to use this. So this theory can be extended to laminar flow. It's mostly important to remember that you have to pay a lot of attention. The Ks are very different if it's laminar. Ks are completely different if it's laminar. The formula is completely different if it's laminar. So you can't just use the turbulent one in a laminar situation. So you certainly want to verify that you are in a turbulent regime if you're going to use the prior formula, which is certainly the one you're going to use most of the time. But we know that for most airflows and ducts and most water flows and pipes, if the sizes are big, that is, in centimeters, not millimeters or micrometers or something, you're almost certainly going to have turbulent flow.